Assalamu alaikum. Now I'll explain to you how to do the vectors experiment or forces at equilibrium. As you know, there are some vectors in the nature and there are some scalars. The difference between the vectors and the scalars, the vector is given by magnitude and direction, like acceleration, velocity, displacement, force, torque. And the scalar, you can describe it fully just only by magnitude, like the distance, the temperature, the density, the volume of an object. In this experiment, the objectives of this experiment, if we are in the lab, so we're gonna first define the equilibrium. Equilibrium means what, and then we will verify reaching equilibrium state by acting on an object by many forces, and then we can find the resultant force, and then we can act on it by another force, equilibrium force, that set it in equilibrium state, and so on. You will see these things in the slideshow, but this one mainly to show you how to do the experiment practically using PhET simulation. Okay, so this is the force table that exists in our labs. So if we are not online teaching, so I'll take you to the lab and then I'll show you this one, and then you'll do the experiment using this one, using the threads, and then you can set the ring in the middle, the ring here in the middle at equilibrium state, and then add the vectors to find the resultant. Okay, if the equilibrium actually at equilibrium state, so the resultant force must be 0. Now in this video I'll use actually PhET simulation to act on the ring. This is the ring. We'll, in PhET simulation, we'll consider the dot in the middle as the ring, and then we'll act on it by many forces. Okay, so we'll act on the ring or the object by, first, part number 1, we'll act on it by 2 forces, and then we'll use a trial and error method to find a third force that is must be set the object at equilibrium state, and then from this third force we can determine the resultant of the other 2 forces. And same thing, we'll do it for 3 forces acting on the object. So we have to follow the link here, PhET link, and simulation, interactive simulation, and then I'll show you the steps that you will do it alone at your home. You will follow this link and you will do same as I'll show you, but I'll not use the values written in your worksheet. I'll use any values just to show you how to use the link. Okay, so now this link, click on it. Before doing the experiment, guys, open the link and play with it many times to be familiar with it, how to get the vector, how to change the magnitude of the vector, the direction of the vector, the x component, y component, sum of vectors, how to move the vector, how to add the vectors graphically using the simulation. All these things I'll show you now, and then play with it, and then you can do the experiment. Okay, after you become familiar, you control it well, and then you can do your experiment. Okay, so now to follow this link, just click on control and then right click on it, left click, not right click. Okay, wait till the simulation open. Now this is PhET simulation. Now you will see many screens, many windows. Go to click what? Explore 2D, two-dimensional vector. Double click on it. You will get this window now. Okay. Now this circle here, this is the circle at the center of the force table. We'll consider it. Okay, so I can change the 0 of the coordinates here, xy. Just I'll move this point and I'll put it here. Just click on it and then you can control it, you can fix it in the middle. Okay, now there are many buttons here, shows you many things. If you click on sum, then you will get the sum of the vectors that you're gonna display them. If you click in values, you will see the values. If you click in theta, the theta will display on the graph paper. If you just click in component, you will see just the components, and so on. Now there are two options we have here. We have this option. This is for Cartesian coordinates. So you can change the vector as in Cartesian coordinates, x component and y component. If you click on this one, so this is polar coordinate, and you can change the vector and polar coordinate. Okay, so just you'll display the angle and the magnitude, the angle and the magnitude, and then you can control the magnitude and the direction. In this experiment, we'll use the polar coordinate, and then again, once when I click on this one, so I fix this one for the Cartesian coordinate. Now click on polar coordinate and then move the object and make it in the center. Now, in the simulation here, you have three vectors, D, E, and F. Our experiment is two parts. Part number one, we'll act on this ring, on this ball here in the middle by two forces, and then we'll use a trial and error method to find their equilibriums, the one needed to set the object under the effect of F1, F2, and equilibrium at equilibrium state, and then we can find the resultant. Okay, and part two, we'll act on the ring here by three forces. Now I'll start the first one, and I'll use different values, not the ones in your lab report. In your lab report, you will fix them as I mentioned to you in your lab report. Okay, but now I'll show you how to do the experiment using any values for the vectors. This is vector D. I'll drag it and fix it here. This is vector D. Vector D actually is the force F1 acting on the ring. Okay, طبعا no need to keep these values here. No need to click this one or the angle. Just only keep the grades here to show you the vector. Okay, and now this is vector number one, this is vector D, and as I told you, vector D is the force F1 acting on the object. Okay, as you see here, F1 given now, or D, its magnitude is 8 and its direction is 30 degrees with the positive x-axis. This is the 30 degrees. This is the angle 30 degrees with the positive x-axis anti-clockwise. Okay, now the components of this vector are dx 6.9, dy 4. So what's the value of the first force acting on the ring is 80 Newton. What's the angle where the force make it with the positive x-axis in the first quadrant anti-clockwise is 30 degrees. What's the x component of the first force? 6.9. The y component 4. Okay, so this force is known completely. Now for force 2, I'll drag this force, I'll fix it here, and I can change it. I can change its magnitude and its direction. So just to click on the vector. So now this is vector or force 2, F2, 9 Newton in magnitude, 125 degrees with the positive x-axis anti-clockwise. Okay, now I'll use the third force. This is the third force, F3. And I'll change its magnitude and direction till the ring now sits at equilibrium. The ring sits at equilibrium means the forces F1, F2 plus F equilibrium equals 0. So the forces F1 and F2 does not equal 0. Okay, but F1 plus F2 plus F equilibrium, the third force F, the vector F, is the sum of these three vectors is 0. So now to set the ring at equilibrium, I have to show the sum of the three forces. This is the sum. I can drag it, keep its magnitude and direction, but you can drag it anywhere. Don't change the magnitude and the direction of the sum vector. Okay, this is the sum vector. See, this is the sum vector of these three forces. Now I'll change the force F3, F equilibrium, the third force. I'll change it magnitude and direction till the sum here of the three vectors D, E, and F, three forces F1, F2, and F equilibrium almost zero. So see, I can move this one this way. See, is it zero now? No. I can make it this way. No. Make it more, change it this way. So this is the minimum value you can get. It's almost zero. The force now is almost zero. So click on S, you will get S 0.6, almost zero compared to 11 to 10 to almost zero. Okay, so now the ring under the effect of DEF, F1, F2, F equilibrium equals zero, occurs almost zero, almost at equilibrium, and the sum of these vectors is approximately zero. Okay, so now can you tell me what's the relationship? So now you have F equilibrium, its magnitude 11, direction minus 100. This is the force needed to balance F1 and F2 to set the object at equilibrium. What's the relationship between F equilibrium, this one, and the resultant force of these two forces? The resultant force of these two forces equal in magnitude to F equilibrium but opposite in direction. So now you know F resultant for the two forces F1 and F2, same as F equilibrium in magnitude but in opposite direction. Now this is F and this is the direction of F minus 100. Minus 100 means this angle. The angle measured relative to the positive x-axis but clockwise, not anti-clockwise. If you want it relative to the positive x-axis anti-clockwise, so actually theta, guys, equal 260. So you record it in your lab report, the one relative to the positive x-axis anti-clockwise. Okay, 360 minus 100, it is 260. So now you know F resultant experimentally, which is almost zero. You know F equilibrium experimentally, magnitude and direction. This is F equilibrium 11 and the angle is 260. And you can now get F resultant, which is 11 in magnitude but in direction must be opposite direction. So the resultant force of F1 and F2 is 260 minus 180. So it becomes in the first quadrant. You know the experimental value for the resultant force of the two forces and the direction, the magnitude of this resultant force, and this is the experimental way to find the resultant force of two forces or two vectors by compare it to the third force called the equilibrium force. That's we determine it by trial and error method, that force needed to set the object at equilibrium state to balance the other two forces F1 and F2 or D and E. Okay, now you can add F1 and F2 graphically. How can you find the resultant? You can find the resultant analytically by analytical method without looking at F. Okay, now you finished the experimental way to find the resultant of F1 and F2. Okay, so you can get this one back, we don't need it, and we can switch S like this. Okay, so now you have these two forces. To find the resultant, guys, analytically, just click on D, you will get dx dy. This is F1x, F1y. Click on E, you will get ex ey, f2x, f2y. Now what about the resultant? How can you determine it analytically? F1x plus f2x, this is f resultant x. F1y plus f2y, this is f resultant y. F resultant x squared plus f resultant y squared radical, this is the magnitude of the resultant of these two forces. The angle where the resultant make it with the positive x-axis is the one you can determine it by theta equal tan inverse f resultant y over F resultant X. So you know now again F resultant analytically. So click on D, get its component recorded in your lab report. Click on E, get the components recorded in your lab report, and then use the trigonometry, use the tan to find the resultant and compare it to the practical one or the experimental one. Now also another way of finding the resultant of many vectors is called the graphical method or head-to-tail method. How can I determine the resultant of these two vectors graphically? Just I can move E and fix it where? On head. Once you move the vector, you have to keep its magnitude and direction. Okay? This is the resultant graphical value of the resultant force. Okay, just move the second vector, put it on head the first one, and then you click on sum. This is the sum. You can fix it this way. This is the resultant force. The resultant force now S is 11.5 in magnitude and makes 81 degree theta, 81 degree. This is 81.2 degree with the positive x-axis. This is where the resultant make it with the positive x-axis. Now take a screenshot for this one, the graphical method. Go to fit here, the three dots, okay, and then screenshot. At the low right corner of the simulation, there are three dots, and written beside it fit. Click on the three dots, you will get many options here. You can go back to fit website, and one of the options is screenshot. Click on screenshot and then copy it and then or print it and attach it to your lab report. Now part one finished. The resultant of two forces. The resultant of three forces. I'll clear this one, and now I have these three forces. Okay, force 1 D, I'll put it this way, and I can change its magnitude direction as you wish. The second vector E, I'll put it this way, for example. Click on sum, remove it, remove this one. Okay, and then this is vector F2. Okay, click on F, this is force 3. For example, this is force 3. Now I have three forces. I want to find the resultant. How can you determine the resultant? How can you determine the resultant experimentally? The resultant experimentally. See now, go to your worksheet and go to part 2. This is part 2. These are the three forces, F1, F2, and F3, for example, different from the one I choose for you now. Okay, now just click on the sum button here, and then you will get the experimental value of the resultant force of these three forces. Right? If resultant magnitude and direction, and then if equilibriant, which is the force needed to balance these three forces, same in magnitude as if resultant and opposite in direction. Just get the values, and then you can easily determine if equilibriant. I'll go back to the simulation, and I click on sum, and then my resultant force of these three forces is this one. Its magnitude 9.1, direction 14.4, S component كالقد Y component 2.3. Okay, now I can determine the click on S after doing this one and getting the values. Now I can click on D and get the components of D, which is F1x, F2x. Click on E and get F2x, F2y. Click on F and get F3x, F3y. Record these components in your lab report. Record the components were here: F1x, F2x, F1y, F2y, F3x, F3y, and the force's magnitude is also, you can get it from here. Fill the table and then find if resultant x. Add F1x, F2x, F3x. This is if resultant x. F1y, F2y, F3y. This is if resultant y. So you can easily now, by trigonometry and the tan function, you can determine if resultant for the three forces and the angle relative to the positive x-axis anticlockwise. Okay, this value is called the analytical value. You can compare the analytical value to the experimental value, the one using the simulation. One more thing, you can do it here to find the resultant graphically. How can I determine the resultant of 3 vectors graphically? From head D, move E and fix it on head E. From head E, move F and fix it on head E. This is F. Okay, so now you have F, it is on head. Okay, the resultant of these 3 forces now is the sum. Click on sum. This is the sum. If you fix it here, this is the resultant force. Okay, this is the graphical method. So graphically, the resultant force is 9.1 in Newton and 14.4 in direction. This angle here, I'll click on theta. So this angle Z, this angle, the small one, is 20. No, it's not a 20, it's 14. I think a 24D. If I remove D, this is D20, so it's 14.4. Okay, now once you finish this one also, you can what, guys? You can go to fit on the lower right corner and then screenshot and then attach it to your lab report. I hope now you can easily do the experiment and you can easily submit it, and I wish to you good luck, guys. I hope I can see you and help you more, but what we can do, again, this is the COVID-19 pandemic. Okay, bye bye and see you.